Hey guys, in this video I'm going to show you how to use the Orbit app in order to do the simulated Kepler's second law lab. So the Orbit app is actually a game. But it happens to use real physics. So this is what it'll look like when you open it up, is what you see in the bottom left corner. In case you haven't downloaded it yet, this is the icon for it on the App Store. So let's say I hit play. For this particular lab, you're going to use level 1 or level 2. Either one is just fine. And if it's your first time playing, it'll give you some kind of a message like that. And then it tells you how to do it, right? So it says touch and hold, such as there. Okay, and then you drag in order to create some sort of an orbit. Cool. And there it goes. It's off. It's going to orbit around the black hole. Now, the game is actually pretty fun to do, but what I'm going to have you actually use it for is to, I can't say to prove Kepler's second law, because of course it's a video game, right? But what you can prove is that the video game follows Kepler's second law, and you can determine some things such as like what must be the mass of the black hole in the center of the screen in order for it to be orbiting like this. I do recommend you play around with it a little bit, just try and see if you can get some, different sorts of orbits going, like this one or that one. Although I will say that when you are actually trying to do the lab, it's really helpful if you only have one thing orbiting at a time. Best way to make a planet crash is just, pop something into existence right in front of it, and didn't quite do it. Let's see if we can crash it. There we go, I crashed that one. Cool, so I'm back down to one planet orbiting at the moment. Okay, now the lab handout is going to be in the drive, so you can take a look at it. There are some questions that it has you answer at the beginning. I'll let you figure those out on your own. I want to cut straight down to procedure here. So in the procedure, it says that you're going to get a variety of satellites or planets, whatever you want to call them, to orbit the black hole. All right, do one at a time. That's what I'm doing right now. And then for each one, you're going to time its orbit using something like a digital timer. Okay, and then once you've got it going, you're going to measure the time for it to make 5 full orbits. So the way 5 full orbits is going to be counted is like this. All right. I'm going to get ready here, guys. Going to get ready. Okay, wait. I'm going to wait for it to get at what I think is aphelion. Ready? And 0. Oh, it didn't actually start going. But did you hear how I said 0 and not 1? That's because if you start counting at 1, then by the time you say 5, like 1, 2, 3, 4, 5, it will actually have made 4 orbits. And you want 5 orbits, because if you measure 5 orbits, right, measure the period for 5 orbits and then divide by 5, that minimizes the effect of human reaction time. Okay? All right, so it's going to come around again. I'm going to wait until it's at aphelion, and then I'm going to go. It was a little late because I didn't know where the cursor was. Oh, hold on. All right, here. It's almost made it one full time around, and 1, because I think that's about where it was in the orbit before. Okay, all right, here it's coming around again, and 2. All right, you get the idea, right? I'm going to count 1, 2, 3, 4, 5, right? Write down whatever time it says when that happens in this first box here where it says 5 periods, okay? And then I'm going to do the same thing for 5 more orbits. Now, don't just measure the time, okay? Let me go ahead and stop this thing here. Okay, fine. I don't know if it actually made 5 orbits or not. I wasn't really counting because I have a different example that I already measured that I'll use. But, let's say, it's made 5 orbits. I've measured and everything like that. What I'm going to do next is take a screenshot of this thing, right? Now, what do you want the screenshot for? Well, what you want the screenshot for is step 2, where it says screenshot the orbit and measure the length of the major axis using a ruler. You could do that by, if you have a way of getting the screenshot onto a computer, such as I have, then you can put it up on the screen and then slap a ruler against the screen. It's a little harder with the iPad since it's a touch screen, but you can probably put a ruler just straight up against the iPad screen and, measure the length of the major axis, and that will work just fine. All right, let me show you what that step is going to look like using a different screenshot that I already have. All right, now here is a different screenshot I made, and I happen to have already measured the orbital period for this one, so I wrote those numbers down. And what I'm going to do now is slap a ruler on there, a digital ruler, because I can, and I'm going to measure the major axis for this orbit. Notice, in this case, I don't have the ruler straight up and down. That's because my visual estimate makes it look like the ellipse here is a little bit tilted, right? And you will probably have that too. Most of your ellipses are not going to be straight, vertical, or directly horizontal. They're going to be a little bit tilted. So let me see. I'm going to line up the 0 very carefully there, and looks to me like the major axis is just maybe a tiny bit over 18 centimeters. Now that I've got measurements for my 5 orbital periods and the major axis, I'll go over to my data table and I'll start filling those things in. Or maybe I've already filled some of those things in. Let's see. Okay, so for this particular one that I already did, apparently the time for 5 periods was 24.799 seconds, and my major axis was 0.1805 meters, meaning 18.05 centimeters. Okay, so I convert that to meters. All right, well, to find the period, divide this number by 5, okay? And then to find the semi-major axis, take the major axis and divide by 2, because the semi-major axis is half the length of the major axis. Okay, now I just repeat that process 4 or 5 more times. Notice there's another row here just in case you're like, one of my orbits is bad, which I'll explain in a little bit how to identify a bad orbit. But yeah, you got to fill out the rest of the table here, right? Take all your other measurements for 4 more orbits, and these are the numbers that I have. Wow, they're coming so fast. Okay, great. So those are my measurements apparently. So I've got 5 different periods and 5 different semi-major axes. Now, what do I do next? Well, what you're going to do next is put your data into Vernier Graphical Analysis. Remember, for you, it's probably Vernier Graphical Analysis GW, but my iPad's really old, so this is the one it runs. We'll tell it New Experiment, and we'll tell it Manual Entry, since it's not collecting anything via sensors. Okay, now, first thing we'll do in Vernier is update some of the names of our columns, which you do by tapping on those 3 dots next to where it says X. Column options. Let's make this first column be period. Great, okay. And then for Y here, we'll change that to semi-major axis. Well, actually, let's just call it little a. Okay, and I guess I'll just call period T, but whatever. Well, actually, no, I probably should call it, yes, we'll call them period and semi-major axis. Great. Kind of wordy, but that's okay. Semi-major axis. There we go. Done. Great. Now, these 2 columns are nice and all, but they're not actually what we are ultimately going to want to graph, okay? So, we'll put in the numbers and such, but you're going to actually make 2 graphs. One of them is going to be period versus semi-major axis, but the more important one is actually going to be period squared versus semi-major axis cubed. Kepler's second law, what? It says Kepler's third law. It should say Kepler's second law. That's strange. Anyway, Kepler's second law says that period squared equals or is proportional to semi-major axis cubed. Okay, so we are actually going to graph those 2 things which means that we need to add some columns. Okay, so let's see, add manual column. And this one is going to be period squared. All right, and then apparently it didn't like that. Okay, next, add manual column again. And this one is going to be semi-major axis cubed. Done. Okay, and then we'll go through and enter those things in. Let me just switch this over to table so that we can read everything we're doing. Okay, and then I will double tap on the box to bring up the data entry, and I'll start entering in my numbers. So let's see, for the first orbit, one period was 4.96 seconds. The semi-major axis was 0.0905. Okay, and then periods squared, I would get out my handy-dandy calculator and calculate what 4.96 squared is. Looks like it's 24.6 roughly, all right? And then semi-major axis cubed, 0.0905 cubed is tiny little number, 0.00074112. Okay, and there are those numbers in. Now, when you reach the end of a row, you might be like, what do I do next? How do I get a new row? You just tell it next. And it will make a new row, and then you can fill it in with all of your other numbers. Okay, I'm going to do that. I'm going to get everything filled out, and then I'll show you what to do next. So here is all of my data filled out, right? These numbers I had over here in the table, and we've got the other two columns here from calculating them in our calculator. All right, now the next step is we got to graph some stuff out. So I'm going to poke that button up there, this one here, and I'm going to tell it one graph. And you may have to make it change the axes. Make sure for your first graph that you've got period there. You do that by poking the axis. And as you add or remove things, you'll add and remove check marks, okay? So we're going to have period versus semi-major axis. You select the x-axis the same way you select the y-axis. And then we will go down to this button here, poke it, and tell it apply a curve fit. And you'll notice that your graph looks like pretty good, like, it's kind of linear if you squint, except for this last data point. Now, your data might not be quite as good as mine, because frankly, I doctored my numbers. So some of them might be a little above or a little below, but this one shouldn't actually be quite linear. Either way, go ahead, take a screenshot of that, right? There it is. And now graph the one that you really want. Since it's t squared is proportional to a cubed, you're going to change the x-axis now to semi-major axis cubed, and change the vertical axis to period squared, and make sure you uncheck period. All right, and so now when I add a curve fit to this, it's very linear, right? You can see, hey, look at that. I mean, that goes through all 5 data points. And if when you graph period squared versus semi-major axis cubed, it doesn't give you a straight line, then you've got some bad measurements. Okay, so go back and check your measurements, or check your squaring or cubing. All right, now, what is all of this for? What can we do with this curve fit right here? Well, what you can do is this. The slope, this part right here, 3.326 times 10 to the 4th is equal to all this other junk on the right side here that is not a cubed. So 4 pi squared over gm, those 4 things equal that number, which means that you can then use that result to solve for the mass of the black hole, which is actually the point of what you're trying to do here. Okay, email me with any questions, and I hope this was helpful.